Ну все, можно начинать. По-английски желательно.
All right, so let's start. Yeah, thank you for invitation. It's really nice to talk at this seminar. It feels like, yeah, for me it feels like continuation of the old seminar, the ATP, which is again really nice. And so for the last few years I've been doing mostly mathematics, and yeah, it's been a while since I've given a talk in front of physicists. So please ask questions. Please interrupt me. Especially since yeah, I'll give some physics motivation, but then I'll mostly talk about some more mathematical aspects of the things, but I hope they will still be interesting. So right, this all starts from so let me first explain what are usual central charges, and well, there are of course many notions of central charges. What I mean by it, and basically here I mean so partition functions on a hemisphere with a round metric, so which is topologically D2, a disk of gauge linear sigma models, supersymmetric, so it's two-dimensional, n equal to 2, 2 supersymmetric theory of chiral fields and vector fields. And the idea is that, right, so this is of course the maximal supersymmetry of the theory. On the disk, there is a n equal to 2 supersymmetries arise on the disk. Because of the boundary conditions. So what's the theory about? Theory consists of chiral fields, which are called big xi's, and this is a superfield in the component field. They have components xi, psi I plus minus, psi bar plus minus. So those are spinors. Then there is some auxiliary field fi, boson, and there are vector fields, vector multiplets. V sub A. So I'll use indexes like ij for chiral field and like ab for vector multiplets. And the corresponding component fields look something like. So there is basically one form, a gauge field V. There is some complex scalar sigma. There are also fermions, just supersymmetric partners of these guys. And there is an auxiliary field as well. And well, so gauge linear sigma models are theories which are sigma models into a vector space, but with gauge fields and with superpotential. So
Kostya, sorry, I runs here from
right. So I and A run some subset. And for now we'll say let's say I goes from 1 to n, and then xi's are coordinates. So small xi's are basically like the images of this, the values of these fields, coordinates on vector space Cn.
So each x is supposed to be complex field.
Yes, exactly. So xi's are complex fields, vi are real fields.
Vi are real.
So right, and A runs from, let's say, from 1 to some other letter. Let's call it kappa. And well, in principle, VA they are in a joint representation of some Lie algebra. But for today, For today, our gauge group is just UN, a U kappa, sorry, U1 power kappa, or a complex version, which I'll call G, is C star power kappa. So it's basically U1 with additional rescaling symmetry. Right, and so what's Lagrangian? I'll write in like the general form of the superfield formalism. So in the superfield formalism, we have coordinates z at zeta bar, so the complex coordinates on two-dimensional wall sheet, and then there are theta plus minus, theta bar plus minus. So those are super coordinates, but this is just some fancy way to write some bulky kinetic terms. I mean, not only kinetic. So the Lagrangian is integration over all these variables of sum over I. So big xi integer, and then e to the v. So v is a gauge field basically, and gauge field acts on the chiral fields. So each chiral field has some charge with respect to one of those, each of those u1s. So this is basically a kinetic term for the chiral fields plus some interaction terms which appear just because of supersymmetry. Then there is this kinetic term for vector fields, and it's written as usually something like sorry. So usually people write some coupling constant, and then oh, it's actually quite bad, but let me actually use a summation notation. Sigma A bar, where, so yeah, I didn't try this. So letter sigma here means superfield strength of V. Of V A, which is which is basically a second derivative of V. So something of this sort. So this is just like the usual kinetic term for the gauge field plus some superpartners.
So may I ask,
of course,
the charges of your fields, where are they hidden here? I mean,
oh yeah, right. They're hidden here. So maybe I can write it like this: Q A I A X xi. So where xi is charged by QAI with respect to VA. Right. Thank you. So there's some remark. And then there are there are potential terms. So those are just classical kinetic terms. And then there are two potential terms, Lagrangian. So, and one is okay, so I'll read the formula, then I explain what it means. Theta times integral d2 theta twiddle times sigma plus integral d2 theta w of xi plus complex conjugate. So what it means? It's a pretty bad notation. So let's call it T. So T, which I'll call omega plus 2 pi I b, is a phi yellow plus coupling constant. Complexified, so this is like theta angle, and this is the real phi yellow plus coupling constant. So this guy over here is called the twisted superpotential. So sigma is the field strength of superfield strength of the vector fields. Actually, sorry, yeah, there is index A over here. It's summation over all the vector fields, and correspondingly there is index A here. So this D2 theta twiddle is, well, there are two holomorphic ones, two anti-holomorphic ones, and here, yeah, actually let me write it like. So there are cross terms. One term is holomorphic, another is anti-holomorphic. And this D2 theta is product of two holomorphic terms. And W is a usual potential, superpotential. Usual Landau-Ginzburg superpotential. So W of x is just a holomorphic function. Usually it's a polynomial. So holomorphic function of chiral fields. All right, so this is how roughly the Lagrangian, super Lagrangian looks like. And what's important is probably
sorry, should it be something like charge zero holomorphic function or something?
Oh, right. Thank you. So so it is charge zero with respect to the group G, to the gauge group G, which is our U1 power kappa, and charge 2 with respect to our symmetry group. So there is an R symmetry. I always forget which one is which. So there is a vector and axial R symmetry that that form automorphisms of our supersymmetry algebra, because there are two supercharges and two holomorphic supercharges, two anti-holomorphic supercharges. So there is a U1 rotating each pair, and then vector symmetry is diagonal symmetry that rotates simultaneously holomorphic and anti-holomorphic pairs, and axial symmetry is the one that rotates them in the opposite directions. And here, let's see which one is which. I think it's vector, because if it rotates d theta and d theta plus and d theta minus by the same charge, then this volume form will have charge 2, -2, let's say, and so superpotential must have charge 2 to cancel that. Right, and if superpotential is not charge 0 with respect to the gauge group, then this is just not an invariant Lagrangian. Also, I think this is not the most general form, so you could in principle add like Keller metric on the vector space. You could add non-diagonal coupling constant for the vector fields. You could, oh, sorry, what happened? Okay, sorry. You could add some more general twisted superpotential, but this is the theory, which is, I think, most interesting that we will consider. And one of the most important things to know from this Lagrangian is basically the scalar potential. So integrating out these theta variables, supersymmetric coordinates, we get scalar potential. Scalar potential U. So scalar potential depends obviously only on the scalar fields. And what are the scalar fields? Scalar fields are xi's, which are scalar components of the chiral fields. So F and D are auxiliary fields, so they can be integrated out, and they have some equations of motion. So then sigma. So sigma is a scalar component in the vector multiplets, and basically nothing else. So that's all that we will find in the scalar superpotential. It will be of x and xi's and sigma a's. And what is going to be? So there will be some term proportional to sigma a's. Times something, which is not very important, plus a more important term, which has the following form. What was my name? My name for the locus parameter was omega a squared. So obviously, as in most supersymmetric theories, the most interesting, or maybe the most approachable quantities to consider are vacuum states. So vacua of the theory correspond to zeros of the scalar potential, and the zero solutions are given by sigma a equal to 0. So it's basically the sum of squares. So yeah, these guys are also some squares. And qai xi squared equal to omega a. And we'll also quotient it with respect to our U1 k gauge symmetry. So spatial vacua is solution to these equations modulo U1 power k, because this is a gauge symmetry. And mathematically, this space of vacua, so U equal to 0, is a Hamiltonian reduction. Oh, right. Sorry. Of course, I missed the not the important term, because there is superpotential. So if there were no superpotential, that was space of vacua. And of course, there is an important term plus sum over I dw over dxi squared. So there is also this. So dw equal to 0.
And B doesn't enter. B, I mean,
It was my earphones. All right, so it's a Hamiltonian reduction plus equation dw equal to 0. So it's Hamiltonian reduction of what? Hamiltonian reduction of Cn, which is a target space for our sigma model, modulo the group U1 power k with the moment map given by qia xi squared, and the moment parameter omega, which is a vector of omega 1 up to omega kappa. So what's Hamiltonian reduction is we take a pre-image of z. Sorry, we take let's call this moment map mu a. So Hamiltonian reduction is is exactly solution to this equation. So pre-image of some value of the moment map divided by the action of the gauge group. And another description, so equivalently, it is geometric invariant theory, or GIT quotient of Cn modulo C star power kappa. So this is just an equivalent mathematical description, which you also might see somewhere in the literature. All right. So now I want to discuss.
So somehow here is important that the number of Hamiltonians, so the number of U's is the same as the number of U1s.
Exactly. Yeah, this was happening because for each U1 we get this term, and so for each of the square in the sum, and so in the moment, in the vacuum equation we have a corresponding equation. So each U1 produces effect like a summand, a positive, a non-negative summand in the scalar potential, and so it produces a component in the moment map equation. Yes. Exactly. Right, and of course I almost forgotten again. So we have equation dw equal to 0, or dw over dxi equal to 0 for all xi. And this is of course a critical locus of a function, like in Gilbert theory. Critical locus of w in our GIT quotient, or in our Hamiltonian reduction. So let's call this Hamiltonian reduction, so I don't so this is the same as this. And let's call it curly x sub, I guess x is a bad notation, right? Because there are so many x's. But yeah, I don't know. Let's call it big M sum omega for manifold. So it's critical locus of a function w, holomorphic function w, in this M omega. So this is the vacuum space of our GLSM, and this is so roughly like in low energy, GLSM describes a sigma model. So in some regime, GLSM describes non-linear sigma model into this critical locus of W in M omega.
So, sorry, but M omega, does it depend on omega? I mean, as a manifold?
Yes, it does. It does depend on it. So in two ways. So topologically, it depends on omega only as in a Walden-Chamber structure. So it doesn't locally depend on omega. If we just change omega a little bit, it doesn't depend on omega. But then there are some walls in the space of all omegas. If we hit this wall, then our space will be singular. And if we cross the wall, the topology will change.
Omega all positive, right? Or not necessarily?
Not necessarily, because if our charges QIs can be both positive and negative. And in fact, it's more interesting when the charges are both positive and negative, and then there are non-trivial choices for this omega. So, all right. So this basically gives dynamic, dynamic change of space of vacuum, right? Because like this omega variables, if you just continuously change them, then your space of vacuum changes as well. And this is how you can get relation between theories with different target spaces. Right. So this description has at least two things which I like about this. So one thing is that this space critical locus of W in M omega can be like horribly singular. Like if it's orbifold singular, it's fine. It still can be thought of as a nonlinear sigma model with some gauge discrete group. But if it can be some really singular manifold. And then there is no good nonlinear sigma model description. But GLSM provides a nice description for all values of omega and for all the values of parameters. So it actually doesn't care if this NLSM is singular or whatnot. And the second advantage is that, well, nonlinear sigma models are hard. There is metric, there is topology, like all these things, which I don't know much about. There is a norm group flow and all these things. And GLSM is a very simple theory because it's a theory basically, and you have a vector space, and then you have some group action, and today is just U1 to some power. And for this reason, GLSM is like exactly computable, at least on the level of massless sector. So in mathematical language, this M omega is a toric orbifold. And in fact, like any nice enough, meaning semi-projective toric orbifold M omega can be obtained as such a GLSM. So we can construct a lot of target spaces. And so GLSM describes a critical locus in like, almost general toric orbifold. So it allows to describe very many nonlinear sigma models. All right, so now I want to say a couple of words about boundary conditions. Boundary conditions. Since we're considering a theory on a disk, obviously we have a boundary which is just a circle. And it introduced some complications, namely boundary conditions. And we cannot just put trivial boundary conditions. We actually have to add some boundary Lagrangian for the following reason. So we have a Lagrangian, and so let's say let Q be the supercharge. Let's curly Q be a supercharge. And delta be a supersymmetry variation. Epsilon Q plus epsilon bar Q bar. And then in order for this theory to have at least some remaining theory on a disk, to have at least some supersymmetry of the whole theory, we need it to be preserved at least by some of these variations. We need the Lagrangian, the action. So we have action, which is integral of our Lagrangian over d2. And then this delta must be equal to 0. And we know that, let's say, on a closed surface, so we know on a closed surface, this integral is 0. So this variation is 0, just because the theory is supersymmetric on a closed surface. It basically says that supersymmetric variation of Lagrangian must be some total derivative. Let's call it something A. So then if the surface is closed, then by the Stokes formula, this holds true. But in fact, this A is non-trivial. So variation of the action on the disk is actually
sorry, but I think that in super space, I mean, if you use thetas, then it is kind of identical. It's not a total derivative. It's just no.
So it turns out that it's not total derivative exactly for this term.
Oh.
So I didn't do the whole computation, so I'm not exactly sure how it works. But
No, I just thought that like the supersymmetry is nothing. I mean, it's generated by translations in theta
Mhm.
space.
Mhm.
And that's why.
Mm.
Well, maybe still. Oh, well, I understand if you integrate our like auxiliary fields or some. If you integrated theta, you mean
At the end of the at the end of the day, you'll get contributions from auxiliary fields.
You mean you integrated first over theta and then
Mm-hmm. Yeah, you first have integrate over theta, and then you'll get the usual Lagrangian, the scalar Lagrangian.
That's what you're saying. I see.
Mm-hmm.
Mm-hmm.
So this Lagrangian is already like this, all integrals over thetas.
Mm-hmm.
And then so actually it's remarkable that in all of these papers about supersymmetric localization on of this type of theories, people don't even bother to write superfields. People write the scalar Lagrangian directly.
Mm-hmm.
It's of course lengthy, but then they write supersymmetric variations, which are also somewhat lengthy, but then there is some computation which actually produces all these results. So like the superfields formalism in this sense is just like it's nice for exposition because you don't want to write like big Lagrangians for for a short exposition, but in all actual computations are done with scalar Lagrangians.
Yeah, and also stupid question. The metric, your disk is flat. You don't have any metric on it.
No, so here it's important actually that metric is round. So round
It's
with round metric.
So it's a half sphere. It's not
exactly. It's a hemisphere.
Hemisphere. So just Fubini studio metric, half of it.
Exactly. So you fix some radius, and this radius is actually it's kind of remarkable. If we have time, I'll tell about how this radius relates with mathematical objects. I mean, it's kind of obvious because this radius is in fact at the end of the day it relates with the volume of the manifold in the Kähler, of the target manifold in the Kähler, in the Kähler form. But yeah, maybe I'll say something about this later. So there is some boundary Lagrangian. It has something. It has some form. It looks something like epsilon psi I d I w. So you see there is this derivative of w, and derivative of w appear only in the when you integrate over the super variables. And I think there is some some different signs somewhere. So there is some boundary Lagrangian. Sorry, there is some boundary non-canceling term in the supersymmetric variation. And so in order to cancel this, people add boundary Lagrangian. So you can engineer some boundary Lagrangian such that its supersymmetric variation is the opposite. So this the expression on top with a minus sign. And then the whole Lagrangian boundary and bulk Lagrangian, the whole Lagrangian will be supersymmetry invariant. So in fact, in order to construct some Lagrangian, in order to construct boundary term, we need, in fact, we cannot construct it for like just scalar fields as is written here. So we need an additional Chern pattern space. Or rather, let me write like this. We need a matrix factorization. of W. So what is this? So you can think about this as a Dirac operator, right? So you have a Laplace operator, and then you want it to be, you want to take a square root of Laplace operator, right? And then Dirac found that you can actually find some operator such that d square is equal to nabla. But then if your dimension is not 1, then you cannot find a scalar square root of Laplace operator. So the Dirac operator is actually sum of gamma matrices times d mu. And you can think about so we can think about a Dirac operator as a matrix factorization of a Laplace operator. So what's matrix factorization? Matrix factorization of W is some vector space, some finite dimensional vector space, is which is usually called Chant pattern vector space. So if you think about this in terms of like of a theory of a theory on a surface with boundary, in the classical language in terms of like strings and the endpoints and boundary condition on the endpoints, then each endpoint of your string can be augmented by additional finite degree of freedom, which will define like some finite dimensional vector space, and this is called classically called Chant pattern vector space. So I'll just put it here, which I'll call E, and it will be sum of E0 and E1. So and then operators, or maybe just maps, like linear maps. Delta 0 and delta 1, which map between these spaces. Which interchange them. So you could think about it, some diagram like this. And then you want their square to be, so you want the similar property, you want their square to be, but not Laplace operator, you want their square to be W times identity matrix. So such that delta 0, delta 1 is W times, so delta 0 maps to E1, so it must be W times identity matrix on E1. And delta 1, delta 0 must be W times identity matrix of E0. So in other words, you can think about like this skew diagonal matrix, like block. So this will be a block skew diagonal with matrices delta 0, delta 1, such that its square, which is exactly let's see, delta 0, delta 1, delta 1, delta 0. And it must be W times identity on E. So you want to take your superpotential and then take somehow a square root of it in terms of some polynomials as well. And usually you cannot take a square root of a polynomial, at least in terms of polynomials. But then if you allow yourself to introduce some additional vector space, like you did in Dirac operator, then you'll get a lot of these objects. This is called the matrix factorization of W. And there are some compatibility conditions. So obviously this whole thing must be G invariant. So delta 0, delta 1 must be G invariant. So they must be charged 0 with respect to the gauge group. and charge 1 with respect to, so because our superpotential has charge 2 with respect to R symmetry, and superpotential is delta 1 times delta 0, or delta 0 times delta 1. So it must be charge 1 with respect to R symmetry. So this is a matrix factorization of W. And so the fact is, if you start from such a matrix factorization, then you can write a boundary Lagrangian that cancels
So
this.
may I ask, so delta 0 and delta 1, so should we impose that each of them depends on all variables xi, or
Yes, they might or might, in principle they depend on all the variables, but they might not be dependent on some of them. I'll give examples like in right. So and the point is that if we start from any matrix factorization of W, then we'll get some boundary invariant Lagrangian. So conceptually, any matrix factorization produces a boundary condition, a well-defined supersymmetric boundary condition for our theory. So now examples. Yeah, maybe I'll give one example for now, and then if it's with time, I'll give some more at the end. Quintic threefold. Or in other words, nonlinear sigma model in the quintic threefold. So how do we engineer a nonlinear sigma model into such a thing? Well, we start with a vector space C6 with coordinates. So start with coordinates x1 up to x5, and the last coordinate we'll call P. Then our gauge group will be just C star, or if you like U1, if you like the real form. And the charges, gauge charges of this U1 will be 1, 1, 1, 1, 1, negative 5. And the R charges will be 0, 0, 0, 0, 0, 1. 2, sorry. There are some different conventions, but so then we can take superpotential of x and p, and we can take p times any quintic polynomial. Let's take a Fermat quintic because why not? So this is degree 0 with respect to g because it's fifth order polynomial in x, so it's degree 5 times something degree minus 5. And then it's R charge 2 because P is of charge 2 and everything else of R charge 0. So now let's see what's going on. What's M omega? So there are two choices for omega. So omega is in fact is a character of our group, or maybe if we can take it, the real valued character, not necessarily the integer valued character. And there are essentially two choices. Let's start with omega positive. So for omega positive, this Hamiltonian reduction or this JIT quotient. JIT quotient is just technically simpler, so I'll just think in these terms. So this is in fact the usual quotient of C6 with respect to C star, but then we need to actually cut off some unstable locus, and this will be of the form C5 minus the origin. So we take out the locus where all the xi is equal to 0, and then it doesn't do anything with the remaining C with coordinate P, then a quotient with respect to our C star. So we'll get a set of 5 homogeneous coordinates up to a scaling, which is P4, and projective space, complex projective space with dimension 4. But then it's actually so there is additional coordinate with weight 5, so -5 of weight -5. So this in fact is a line bundle, total space of the line bundle, which is called of -5 over CP4. So total space of a line bundle over CP4. So it's a 5-dimensional complex manifold, 10-dimensional real manifold, and this particular bundle is there is a canonical bundle of 1, the classical bundle of 1, and this is just of 1 power -5. So now what about the critical locus? Critical locus or equation dw equal to 0. Oops. dw is equal to dp times the quintic polynomial plus p times d of the quintic polynomial, which is, let's say, let me write it explicitly, I from 1 to 5, 5xi power 4 dxi. And it must be 0 as a differential form, or in other words, each partial derivative must be 0. So since dp is never 0, then sum of xi power 5 must be 0. And now since, well, in order for this sum to be 0 differential form, all the xi's must be 0. But all the xi's must be 0 is a forbidden point in our adjative quotient. It's not a point in CP4. So actually this is also never 0, so p also must be 0. So equation dw equal to 0 is the same as saying p equal to 0 and sum of xi equal to 0, xi power 5 equal to 0. All right. What does it mean? So p is this coordinate, this additional 6 coordinate, which becomes a fiber of our line bundle. So p equal to 0 is just CP4. It just takes the 0 fiber of this line bundle. And then sum of xi equal to xi power 5 equal to 0 is just the quintic equation in the CP4. So this produces the quintic threefold in CP4. So this is what's called geometric phase. Of GLSM. Because its low energy limit is a non-linear sigma model in a perfectly valid smooth manifold. And so the other choice for stability condition is omega negative. If omega is negative, then our m omega, which is kind of space of vacuum without superpotential, so it's going to be C5. Now we don't do anything with x's. We allow all possible x's, but now we do not allow p to be equal to 0. So we remove 0 from the part with coordinate p. And then again, we take a quotient with respect to the scaling. And so now we can basically take a quotient. So we can fix variable p to be 1 by this C star, by this rescaling. But since p has weight -5, if the group element in this C star is a fifth root of unity, then p doesn't change, but x do change. So in fact, the result is not just c power 5, but the result is c power 5 orbifold divided by z5, which acts diagonally by multiplication of each of the coordinates by fifth root of unity. And superpotential is just sum of xi's because we fixed our variable p to be 1. And dw equal to 0 is just, well, sum over I 5xi power 4 dxi equal to 0. It just implies can you hear me now?
Yes.
Okay, yeah, sorry, something happened with my earphones again. Right, so in this case, we have an isolated critical point at the origin, and this is a usual LG model on the C5 mod Z5, and this is called LG phase. Of GLSM. All right, and so for example, yeah, together with Alexander Abramich and Losha, we did a bunch of computations of not hemisphere, not a disk, but sphere partition functions for GLSMs in Landau-Ginzburg phases. But then it turns out that some of the things are actually easier and maybe even conceptually better to compute on the level of hemisphere partition functions. That's one thing. And another thing is that you don't actually need to restrict to Landau-Ginzburg phase. You can actually compute them for any phase. But then I'll tell about it a bit more later. So now I want to say what are these matrix factorizations in this case. So before I said that boundary conditions for these theories, they correspond to these mathematical constructions of matrix factorizations of this Chern pattern vector space with a map on it. So what are matrix factorizations in this case? And they're very simple. So in geometric phase, we can take the following very simple matrix factorization. E0 is equal to C, just one-dimensional complex vector space. Everything is complex here. E1 is also C. And then we need two maps. Well, what would be a pair of maps such that their product is equal to our superpotential, W is P times sum of xi power 5. Well, the simplest choice we could take is just one map is P, and another map is sum of xi power 5. And it turns out this works. So you can think about our matrix factorization as being described by this 2x2 matrix. And when you take a square of this matrix, you obviously get just W, 0, 0, W. So identity matrix times W. Okay. So now you can ask, well, yeah, this is certainly matrix factorization, but then it doesn't satisfy the invariance properties. So I said that it should be invariant, and then there should be some R-charged condition. Where was it? Right, this mass must be G invariant and charge 1 with respect to R symmetry. And obviously map P is not G invariant itself, because P is just gets scaled by G, and P also gets scaled by the R charge with R symmetry with R charge 2. So we actually assign charges to these vector spaces. So for example, we can assign to one vector space charge 0 with respect to the gauge symmetry and 0 with respect to R symmetry. And then to this space, we'll have to assign, so to make all this stuff satisfied, we'll have to assign, so P is charge -5. So this has to have charge 5. And this C has to have charge 1 with respect to R symmetry. Then this whole thing will be invariant. And in our Ginzburg phase, we can do the following matrix factorization. Right, and what I want to say is, in fact, all the relevant matrix factorizations that we get are obtained by taking this one and just changing simultaneously changing the charges of these two spaces. So it's actually, this is kind of a general matrix factorization in the geometric phase of the quintet. So now in the Landau-Ginzburg phase, it's a bit more complicated. So we can define alpha. One map alpha is sum of dxi's, where those are just differential forms of our coordinate xi's, and beta to be, let's say, p times xi power 5 d over dxi. And then our space E, space of Chern-Paton space, is just space of differential forms on X. So the C5 with coordinates X. E0 will be only even degree differential forms. E1 will be, even. E1 will be odd degree differential forms on C5. Well, and then our map, let's say D0 plus D1, because now they're kind of intermixed, all the differential forms as odd and even, it's unnatural to just distinguish between even and odd. So the sum of these maps is just alpha plus beta. Maybe over 2. Over 2. So then the square, no, sorry, I think we don't need the 1 over 2. Square is just anti-commutator of alpha and beta, which is, since anti-commutator of dxi and d over dxi is 1, we'll get just w times identity. So those are just examples of the differential forms, sorry, of these matrix factorizations. And now,
Question, may I ask, I mean, just to have a, to have a picture. So this matrix factorization, so do you mean that you will, your boundary Lagrangian, you have to introduce kind of auxiliary variables which
Exa-
will be in this E node and E1 and
Mhm, mhm.
couple them to your degrees of freedom such that once you integrate over these auxiliary fields, then you will get exactly something
Right, so
like this.
So it's rather like auxiliary construction, not a field, because there are no additional fields, because E1 and E0 are just fixed vector spaces.
No, I'm just wondering, you say I assign charge to a vector space. I don't
Mhm.
see how can you assign a charge to vector space? It's just for some formal thing, or it is
No, it's not a field. So basically, if you have some field that has values, let's say you have some open string, then its boundary is lives in this vector space. Then what does it mean to assign a charge to a vector space? It means that when we act on this on any field with values in this vector space, we shift its charge by the charge of the vector space.
no, that I understand. Of course. So you still mean that there are some kind of boundary degrees of freedom which are charged. I don't know this.
There are no additional degrees of freedom really. It's like just when you act by your group on something. So when you act by your group on something like on a matrix, in this let's say, so this matrix, it contains no additional degrees of freedom, right? It contains only this P and X, but when you act with your group on this matrix, you act not as on just with charges of P and X, but you also act with the charges. So you shift the charges by the ones coming from. You can think about it as just some shift of charges of objects that enter this vector space.
Mm-hmm.
So there are no
Yeah, but
additional degrees of freedom.
physically, I mean, who's living this vector space? Who's supposed to live in this vector space?
Physically, it's like it's boundary conditions of the open strings.
So these are D-branes. D-branes live in this thing, right? And they charge. Okay.
Yes. Yeah, I mean, if you think about your wall sheet theory, then these are not dynamical degrees of freedom. But if you think about like
I understand.
the brains has some degrees of freedom, yeah, right.
But here, but also here, then you see that this is.
So here there are no additional degrees of freedom. It just so here, what does it mean, like on the level of computations with Lagrangian? So you have your Lagrangian. Where is it? Here Lagrangian, and then you add some. So you add some stuff, including this like Q, some I don't know psi Q, some Q dash or whatever, right? Oh, not Q. It's this delta 1 delta 0 plus delta 1, delta 0 plus delta 1, this stuff, right? You just add this objects into Lagrangian, and when you apply your supersymmetry transformations, when you apply any other transformations, you remember the charge of these guys. So this guy will be some matrix, right? So this will be this delta 1 delta 0 are not some independent fields. They're just matrices with coefficients depending on the other fields, right? So you have this P, this Xi, and those are chiral fields. So there are no additional dynamical degrees of freedom. But when you act with a supercharge or there's anything else on this matrix, so you twist the charges of these components of this matrix by the ones that come from the definition of this vector space. It's like on the level of Lagrange, you don't introduce any dynamical degree.
Yeah, I understand, but in principle, I can substitute in this I can take, I don't know, trace of this matrix with some. So if I have so this matrix X in vector space, then I can take the trace of this vector space with some formal variables. I don't know, whatever. Xi, for example, in this Xi, just by definition, will have these charges.
Right, but this matrix coefficients, they will be just some functions, some fixed functions of your chiral fields.
Yeah, that I understand.
Exactly, yeah.
And here in the last example, it's different, right? Because here your
Oh no, it's just a way to write the matrix. You can just write it in terms of a mat. You know, if I try to write, so this is a vector space which is just what's its dimension? It's like 5 times 4 over 2. It's 10-dimensional vector space, and if you just want to write as a matrix, it's a mess, right? But here you can just write it in a simple way using this notation. It's just so here is just convenient notation. It's just so those are just things that are charged like dxi and commute like dxi. They're not. So to my understanding, there is no like hidden meaning in these variables. It's just mathematically some causal complex of these two guys. But
well, I should say that in principle, the one form is something like, so it should correspond to theta, I guess. No.
No. So here it is literally like it doesn't have any additional meaning except for they commute and they just happen to, yeah. I think I'm correct here, but again I can be wrong, but I think I'm correct here. All right, so now I can compute the partition function. And for this series, and it was computed by Hori and Roma in the 2013 on the paper where they basically repeated like computations done by Peston, by in Krasov, or in two-dimensional theories by Benin Cremonesi and some other people, but for theories of boundaries. And the result is so the partition function on a hemisphere. So now you actually need to insert. So this B here is a matrix factorization. So it's like E delta 0 delta 1 for a brane. And this is what? This is integral over d sigma. So d sigma can be multivariable. And this is a zero mode of the sigma appearing in as a scalar component of the vector field multiplet. So it's so product over A d sigma A. And there will be some contour, which is some purely imaginary contour shifted by some variable. And then there's going to be one loop determinant. And what's one loop determinant? One loop determinant is obviously just product of gamma functions. And this is one loop determinant comes from chiral fields. So this is QIA sigma A plus alpha I, and I'll tell what this alpha I is, times the classical action, and the classical action comes just from the twisted superpotential. So this is the Fayet-Laplace term times sigma, and in general this will be sigma TA sigma A, and times the boundary Lagrangian, which I'll write as Chern of B. So this is familiar to people who saw the formula for the hemisphere partition function. Oh, sorry, for the sphere partition function. But this looks much simpler, except maybe for this Chern character of B. And this has much better properties in some sense. And the sphere partition function can be obviously reconstructed as a pairing of those two guys. So you can think about these objects as mirrors of integral periods on the Calabi-Yau manifold. And the sphere partition function is obviously a Hermitian form of integral periods. So now what's Chern B? Oh, all right, what's alpha I? So alpha I are R charges. R charge. Plus, we can introduce some additional flavor symmetry variables. Acting on our CN. So you can think about them as equivariant variables. And they're very convenient for computations. And if you want to get the usual partition function, you can just send limit epsilon equal to 0. But they're very, very convenient, because otherwise it will be higher. So one can use these variables to separate higher degree multidimensional poles to the just normal crossing divisors. So what's what's this Chern beta? This is pretty much a Chern character of this matrix vectorization. Equivariant Chern character of E. And in fact, it depends only on this vector Chern pattern vector space. It doesn't depend on this on these bundles we choose. Sorry, on these maps delta 1, delta 0 we choose. And it is also equal to just trace over this space E of exponential 2 pi I sigma, which is, if sigma, you can think sigma is a Lie algebra element, which is R kappa, which is Lie algebra of U1 power kappa. Then e to the 2 pi I sigma is a group element, because we exponentiate Lie algebra element. And then obviously it acts on the vector space with respect to its charges. And we also need to account for the R charges. So it's pi I times R charge. So this is R charge group action. And this is gauge group action. So let me write the formula. What happens with the quintic with, let's say, with so it will be simpler to, yeah, but we can actually do both. Say geometric phase of our quintic GLSM. So we have only one U1, so we'll have only one variable, d sigma, and the contour will be just IR plus maybe plus some shift. And we have 6 gamma functions because we have 6 chiral fields. Each chiral fields produce one loop determinant in here. So this is some localization computation of the Coulomb branch of this area. And there will be phi 1. So first 5 fields are charged by just 1 with respect to the gauge group. So we'll get gamma of sigma plus alpha I. And the final field is charged with this charge -1, so -5. So we'll get -5 sigma. Then we get R charge over 2. R charge is 2, so we get +1. And then I get plus alpha 6. Oh, actually, let's call this, yeah, this is like epsilon I. It's not too important, but okay, those are all the gamma functions, all one loop determinants. Now there is a classical action. Classical action is, again, there is only one Fourier-Laplace parameter. There is only one sigma, so it's just e to the t times sigma, 2 variables, and times the Chern character of our brain and what it is. So it is a trace over E of this group element. And let's look at first at geometric ones. So remember that geometric brain, so geometric matrix vectorization is just C and another copy of C. And there are two maps, P and some xi's. And this was charged by 5 and 1. This was charged by 0 and 0. So we get two factors. So trace produces two factors from this C and this C. And the one charged with 0 will be just 1, because it will be exponential of 0. And the one, so here, the R charge is 1. So we get a minus sign, because we get e to the pi I times 1, which is minus 1. And then we'll get e to the, well, 5 times 2, 10 pi I theta. And this is a hemisphere partition function for the quintic for this brane. It's a very simple expression. So maybe in Landau-Ginzburg brane, I'll just write down this trace. I won't, maybe there is not too much time.
I think your headphone is over. You don't hear us. Can you hear me now? Да, yes, now it's here. So
Oh, sorry.
probably,
Where
probably,
did
yeah, probably then you started to explain the character of Landau-Ginzburg brane. So
right? So basically, for Landau-Ginzburg brane, what happens is that so the vectors again maps d0 and d1 do not matter in this partition function. So we only care about the space and the weights on the space. And the space is just space of differential forms, like of all possible degree differential forms on C5. And then degree 1 differential forms, they have R charge 1 and gauge charge 1. So each degree 1 differential form contributes e to the minus e to the 2 pi I sigma. And so all the differential forms can be counted by 1 minus this power 5, because when we get, combinatorics of multiplying 5 brackets, we get all possible differential forms. So these computations are very simple with these matrix factorizations. And what's also important is that this function, partition function, is additive in this brane. So if we have two matrix factorizations, two branes, we can just take the direct sum, which is, well, we take one vector space, another vector space, we just add them up, so I get a bigger vector space, and then the maps naturally comes from this vector space. This will also be a brane. And if you take such branes like this, then the result will be just the sum of the partition functions. So 0 of B1 plus B2 is equal to 0 B1 plus 0 B2. Sorry, there is no direct sum. It's just sum of two functions. Right, and these partition functions are just functions as well. So now, in principle, if you take some basis of branes, then you'll get some basis of periods of the mirror integrals, for example. and then you can construct like sphere partition functions or anything else you like out of those guys. So, right, and the trick here is to notice that since it's a trace of these things, that all the terms that you get are exponentials of some factors of 2 pi sigma. So basically, we can compute all ZB for all matrix factorizations by just starting from basically C with charged by 2 charges, like T is already used. Let's say K and N, and then this will contribute a factor of exponential of 2 pi I K sigma minus 1 power N. So if you know your partition function for such a thing, which is not a matrix factorization by itself, it's just a vector, it's just a one-dimensional space charged by 2 charges. But knowing these guys, you can compute all possible partition functions for all possible matrix factorizations. And I'll call this just CKN. And these guys can be very easily computed by residues.
So, but somehow the polynomial W already disappeared.
Exactly. So polynomial W here is in two places.
Mm-hmm.
First place, it's here hidden in the R charges, because R charges, they somehow fixed by the polynomial, right?
Mm-hmm.
Up to the gauge transformation. That's one thing. And another thing is that the theory is invariant with respect to deformations. Like, for example, Gromov-Witten theory is invariant of the quintic is invariant with respect to the deformation of the quintic polynomial. So you can take any quintic polynomial, get the same answer. And the second place where it enters is exactly this matrix factorizations. So the particular choice of this Champagne vector spaces is governed by superpotential. But you're right that in fact, so when you, for example, reduce to this thing, and when you take arbitrary parameters epsilon, then you can compute partition functions for all superpotentials starting from these building blocks. So that's the point. So these are building blocks for all for any superpotential. But if you remember, for example, the computations of the sphere partition function, then superpotential enters only in R charges. It doesn't even enter on the level of branes, because branes are already like summed over. But here, here you have like additional place where they appear. All right, so do I have like 10 more minutes?
Yeah, sure.
So yeah, I just want to say a couple of words about these elliptic central charges. So maybe before I want to say that now these integrals, they can be computed by residues. And the computation is in fact simpler than for hemisphere partition, simpler than for the sphere partition functions, because these additional brane factors, they don't really contribute. So in fact, you can compute the partition function for such a building block, and for a given building block, it's just a shift of the Kähler variable by this 2 pi I, by Fayet plus parameter by 2 pi ik. And the gamma functions, there are less gamma functions, so there are less things to worry about. And we have been able to compute this partition function. Yeah, the paper is still not on archive, but I hope I've been feeding many people with news that it will appear soon, but now hopefully it really will appear soon. That we have computed these partition functions for all abelian Calabi-Yau cases. So basically, when your vacuous space is a Calabi-Yau, even singular, like any n, any sigma, and any choice of stability parameter omega in geometric phase or in Landau-Ginzburg phase or in any mixed phase, you can get some explicit power series answer. And the computation is by multidimensional residues. And there, this deformation by this flavor symmetry is very important, because if you don't deform, then it's really hard to work out this higher dimensional residues in higher dimensions, but then you can always take the limit of this guys equal to 0. So maybe just an example for the quintic. So geometric and Landau-Ginzburg. And in Landau-Ginzburg, the expression is known for at least some people in the audience, or at least I wrote very similar expression a few times. So basically, then the residues come from these gamma functions. There is only one gamma function with residues. It's all very simple. So we get sum over n from 1 to infinity, and the sigma is what? Is like n over 5 plus epsilon 6 over 5. So it's a residue of this pole, and then we'll get product 1 to 5 gamma of sigma, of n over 5 plus epsilon 6 over 5 plus epsilon I over n factorial. Then we'll get a minus 1 power n exponential phi u plus parameter t times this n plus epsilon 6 over 5. And here actually the contribution from this ckn will be just very simple. Again, it's just shift of this phi u plus parameter t in the imaginary direction. It's nothing more. It really doesn't make things more complicated. So this is z ck 0, let's say, and maybe minus 1 power. This is bad. Let's call it m. Then it's minus 1 power m as well. Right. So this is the expression of the form people know, and for geometric phase, it's also very simple if you introduce these additional parameters, because what happens is that like each of these gamma function can contribute a pole, and then what we get is sum over I from 1 to 5. So there will be 5. So the difference will be basically that here we have one sum, and here we'll have 5 sums of residues. It will be sum over n from 0 to infinity now. And now sigma will be equal to negative n minus epsilon I. It will be sum minus 1 power n, product j not equal to I up to 5, gamma of minus n plus epsilon j minus epsilon I over n factorial, e to the, again, t plus 2 pi ik. Let me actually move it a little bit. Now there will be different, of course, n, so it will be just negative n minus epsilon I, and a factor of minus 1 power n. And that's it, basically. And you have similar formula for all higher dimensional cases. So if you don't introduce these additional deformations, then you'll get higher order residues, because this gamma function will have a pole, and then it will become a mess. But here you can just take a limit and then compute it in this way. So, and finally, the last thing I wanted to talk about is, these elliptic central charges. Right, so central charges. So these things are called central charges because if this two-dimensional n equal to 2 supersymmetric theory is a part of some string theory, let's say you have some, you need central charge equal to 9 in conformal field theory to build a 4-dimensional string theory, then you can start from a gauge linear sigma model of central charge 9. Calabi-Yau theory, and use it as an ingredient in construction of a string theory. Then you'll have, if you compactify on your 6-dimensional space defined by this gauge linear sigma model, then you'll get a 4-dimensional n equal to 2 supersymmetric theory, which you can use to, which will be effective 4-dimensional theory obtained from the string theory. And then this effective theory is n equal to 2 theory, so its supersymmetry algebra has a central charge. And you will have, so these branes, which we'll talk about, this matrix factorization, they will define point particles in this point BPS particles in this 4-dimensional space-time in effective theory. And these partition functions will be exactly the central charges of these BPS point particles defined by these branes in the 4-dimensional effective theory in the resultant string theory. That's why they call central charges. Now, elliptic central charges. The remaining couple of minutes. So I won't go into any details. I just want to give an idea of what's going on. So now we can state with our 2D 2,2 supersymmetric theory and upgrade it into a 3D 2,2 theory on a disk times S1. So now we think about a 3-dimensional theory, but which is very close to 2-dimensional theory because it's a disk, same disk, multiplied by S1, which we think about as a small circle on which we can compactify. And the picture is like this, right? So it's a 2-dimensional theory and then a 3-dimensional theory. The boundary will be a torus because it will be S1 cross S1. So boundary is a torus now. And when I started to think about it, I started to look at physical literature because there are some computations of partition functions on this D2 cross S1 by a few people, which then have been used by Jokers, Myers, and collaborators to construct some K-theoretic central charges or whatever. But then somehow in the physical construction, there are some limitations, let's put it like this. Basically, I think the boundary conditions people managed to put in the torus are too weak. So I tried to do their computation to generalize a little bit. So the theory is more or less the same, right? So you have chiral fields, you have vector fields. So additionally, you have so it's chiral fields, 3D, of course, multiplets which are different, plus vector fields. But now you'll also have plus Chern-Simons action, because in 3-dimensional, if you have a gauge field, you can have Chern-Simons terms, which also affect the action. And so the thing is that after I did a bunch of computations in the physical framework, I just decided to try to guess what would be the correct expression for the partition function on the D2 cross S1. And correct in a sense that, well, so side of the story which I didn't talk about is that this partition function has actually enumerative meaning. So this is some generating function of quasi-map invariants, which are basically like vortices in the physical language. And this is a theorem we managed to prove that this is indeed like this function indeed coincides with some generating function of this quasi-map invariants. And the proof is exactly by computing this power series and matching power series with the quasi-map count. So, and in 3D, you also have analog of quasi-map. You have K-theoretic quasi-map counts. And what we did is, yeah, we managed to find some expression which conjecturally is a partition function of this of some sort of such a theory, which coincides with this generating function of this quasi-map counts. And it also has a very similar form, but has a nicer interpretation. So now you'll have an elliptic brane, which I'll say a couple of words about. And you'll have a very similar integral, but now your integral will be over the compact torus. So before it was over the imaginary real part of your Lie algebra, but now it's really your Lie group, maybe plus shift. Some variables, and S is like e to the sigma, so it's a group variable. And now you'll have some product of Q gamma functions, basically of similar arguments. So I don't think I have details to write about this. Sorry, I don't think I have time to write the details now. But now there is an additional factor, which and there is a variable z, which is a group variable corresponding to the phi Ruppel's parameter. So Q stands for so Q is a radius of additional circle in the three-dimensional theory. To be more precise, it's not e to the sigma, but it's q to the sigma, but this is actually e to the t. So, and this is some product of theta functions. Theta functions involving the group variable S, which is analog of the chiral field, of the component of the vector field sigma, and Z, which is analog of what's it called, phi Ruppel's parameter. So in some more technical language, it is in some elliptic homology class. That satisfies some properties. So what's interesting about this is so this expression is fundamentally elliptic, and it's natural because the boundary of the D2 cross S1 is a torus, so it's an elliptic curve, and so all the objects in this kind of partition function, they must be related with this torus. And so far, so we got some nice mathematical results, but it would be nice to understand this better in terms of partition function of such a theory. Yeah. So and this elliptic homology class is natural generalization of this matrix factorization. So this should be sort of as an elliptic brane associated to the theory. Right. So yeah, sorry for going over time, and thank you. I'll stop here.
Thank you. So this elliptic homology class, it coincides with something which is defined in different terms, or what? I mean,
no, actually, what's going on is, so this elliptic homology class is something we just engineered. But then, so how does it coincide with K-theoretic quasi-map counts?
Yeah.
So when people think about enumerative geometry, like mathematicians who talk about enumerative geometry, they usually think about like this given tal I function and given tal j functions. And so and those are like these generating functions, those are generating series of these invariants. But they're physically not very easily satisfying, because what are they? They're basically, so they're not functions. They evaluate in cohomology or like K theory of your target. And they are, and in some sense, this is fine. This is like a non-specified boundary condition, but they are also, how to say it? Like, you know, if you work with hypergeometric functions, there are two ways you can write a hypergeometric function, right? You can find it, or you can write it in rational normalization when all of your coefficients will be rational numbers, or you can write it in the gamma function normalization. And the gamma function normalization is very nice because it has integral representations and it has some nice connection formulas. It's much more useful than a rational normalization in some sense. And this INJ function, there are somehow these rational normalizations, but also like not fixed function, but some bunch of functions. And in two-dimensional theories, people found out that you can write the central charges which produce this correct gamma function normalization of these functions. And they also have both physical and mathematical meaning because the central charges, they are mirror to the period integrals over integral cycles in the Calabi-Yau manifolds or whatnot. But in three-dimensional theory, like in some particular case, in homomorphic symplectic setting, like there is this business of elliptic stable envelopes, which is like this correct, Q gamma function normalization. Oh, here it's like elliptic function normalization of these objects. But in the general setting, like in this n equal to 2 theories, to my understanding, there was no good way of introducing this unlock of central charges. And so what we did is we took the INJ functions. I mean, we kind of modified it as well a little bit because our theory is somewhat more general. But so we basically took these functions in the literature, and then we tried to think about how to get an integral representation for them. And it turns out that the only natural way to get an integral representation is to introduce an elliptic homology class, because otherwise you'll just don't get. You can get some function, some power series, but you don't know how to write it in terms of some integrals, right? Except for maybe mirror integrals. And so what we did is we found an object which you need to introduce to get some integral representation, and we found this integral representation. And this object turned out to be some elliptic homology class.
Mm-hmm. Thank you.
And this is roughly like if you heard like talks about elliptic stable envelopes, it's some analog of elliptic stable envelopes, but yeah.
So another questions?
Right. So this is basically this the paper that appeared on Archive like a couple of weeks ago is about this elliptic central charge. The actual paper about the simpler subject is still not out. The usual central charges.
Okay, then thank you. I'll stop.